Hello again. I'm Nick Leifker, and welcome to Management 409, Operations Management. Last time, we looked at blocking, and we looked at starving, and we saw how these two combined resulted in this idea that whichever step in the process is our slowest, in other words, whichever step in the process has the smallest throughput rate, can get stuff out the slowest. This would limit how much the entire process could get done. So, when it comes to our process, there's several things that we need to measure. There's several things that we view as important. So, some important measurements. First, what we call inventory. And inventory, the definition can change a little bit, but a good way of thinking about it is it's the number of items contained within a particular location at a particular time. If it's an inventory step, it's the number of items that are stuck at that location. If it is a process step, and this is what we deal with more often, this is the number of items that we can work on at one time. So think of this as work in process. This is how much we're getting done at one time, how many items we can work on at one time. Then there's flow time, and flow time is simply the amount of time from beginning to end to complete a particular item, to get a particular job done. So if it takes 9 minutes to bake a loaf of bread, that's a flow time. That's a flow time of 9 minutes. And then there's this last one, throughput rate. Sometimes it's called flow rate, but I prefer the term throughput rate to distinguish it from flow time. And throughput rate is churn. It's how fast we're able to get stuff out. It is the rate at which the process, or a step in a process, can deliver output, can get stuff done. This is how fast we get stuff done. So needless to say, this throughput rate, this is what we're going to be concentrating a lot on in this particular chapter, because this is how fast we get stuff done. So this is how we measure how much a step in a process can get done, and then, by extension, how much the process can get done. Now, there are a couple of other measurements that we do encounter on occasion, depending on the situation. For instance, we have this idea of inventory turns. You'll oftentimes see this in accounting. Inventory turns is how often in a given time period that the entire contents of the inventory of a certain location are completely replaced. Now, since flow time represents the average time that an item spends in inventory, inventory turns is, in general, the inverse of this flow time. So inventory turns may equal 1 divided by the flow time. Now, we do need to be careful about how we view this because, well, numbers are almost never just numbers. So if flow time is in days, inventory turns is per day. So just something to think about. And then there's cycle time. Now, cycle time we see sometimes as the amount of time between items leaving a particular step in the process. So how long does it take between one item leaving a particular step and the next item leaving that particular step? Cycle time we generally view as the inverse of a throughput rate. Now, you do see cycle time every so often in calculations. We won't deal with it so much here, but you do see it on occasion. And cycle time is just the inverse of the throughput rate. So if throughput rate is items per hour, then cycle time would be hours per item, hours between each item, each successive item leaving that particular step of the process. That said, I do want to go back to this idea of throughput rate. And we'll be mentioning throughput rate a lot in this chapter because throughput rate is how fast can we get stuff done? How much can we get done in a particular set of time. So throughput rate is a measure of capacity. It's how much a particular step in the process can get done, and ultimately how much the process can get done. So, for a particular step, independent of those other steps, how much product can this step churn out? Now, I mentioned before that whichever step in the process has the smallest throughput rate, this is our bottleneck. This is what limits the throughput rate for our process. So, whichever step in the process has the smallest throughput rate, that'll be our bottleneck. So barring outside influences such as demand or supply, and as we've seen, those outside influences can come into play sometimes. The bottleneck determines the throughput rate of the entire process. Now, ideally, what we want with a process is we want a balanced process. We want each step to have as close a throughput rate as possible. That way we don't have a lot of starving and blocking. We don't have cases where a step in the process really doesn't have a lot of work to do. It's just sitting around doing nothing because there is no work for it. So what we want is we want more or less an even distribution of the capacity of the throughput rate through the entire process, including the demand. So, I've mentioned before this idea of inventory, that, how much can a particular step in the process work on at one time. I've mentioned flow time, the time that it takes from beginning to end to complete a particular item. And throughput rate, churn, how fast we're able to get stuff out. Now, the reason why these three come up is because they're mathematically related. There is a mathematical relationship, a law, between inventory and process, flow time, and throughput rate. It is simply Little's law. Inventory equals throughput rate times flow time. Or, to put it in much shorter format, I equals RT. Little's law always holds. Now, you have to be careful as to the numbers you use, but Little's law always holds. This will become an issue when we start looking at the difference between a designed throughput rate, in other words, the throughput rate at a step in a process, if it's not being blocked or starved by anything, and an actual throughput rate, how much is actually going through that particular step in a process. As I mentioned, Little's law always holds. However, if the actual throughput rate is less than the design throughput rate, that means that some other things have to change in this equation too. So if the throughput rate is smaller, the actual throughput rate is smaller, that means that either the inventory is smaller or the flow time is greater. In other words, the flow time is longer. It spends more time at that particular step. Usually what ends up happening is it's inventory that's smaller. The average inventory is smaller. So if we have a throughput rate that is an actual throughput rate that is half of the design throughput rate, well, that means that half the time this particular step isn't busy, isn't working. So you might have a case where half the time inventory is 1, half the time inventory is 0. It's not working on anything. Well, the average of that would be 1/2. That's an example of Little's law holding even though the numbers have changed. It just means that because the actual throughput rate is smaller than the design throughput rate, it means that other parts of this equation have changed as well. So remember, Little's law always holds. Now, the beauty of Little's law always holding is that it gives us a tool by which we can manipulate the process. Because of these 3 performance measurements, only 2 can be chosen by management. The third will be given as a result of the first 2. So if we choose what our inventory is, the number of items we can work on at one time, if we can choose the flow time, so flow time is 8 minutes, well, this gives us the throughput rate. The throughput rate is mathematically calculated by choosing the first two. Now, it also gives us a blueprint by which we can improve the process, depending on how we want to improve it. Now, suppose we want to reduce inventory, and we'll talk about inventory a lot in the course of this particular course. Inventory is a lot like fat. You need some to survive. Inventory is the energy by which your business runs. However, too much, and it can weigh your company down. It can ultimately cause it to shut down. So, we have to be careful with inventory, and sometimes we want to reduce it. So, suppose we want to reduce inventory. Well, if we hold the throughput rate constant, how fast we get stuff out, that means that we have to reduce the flow time. We have to reduce the amount of time that we're working on a particular item from beginning to end. Now, suppose we can't reduce the flow time. Suppose flow time is constant. For instance, suppose we have a recipe where we're baking bread. It takes 9 minutes to bake a loaf of bread. We can't change that. Well, if we can't reduce the flow time, but we want to increase the throughput rate, we have to increase the inventory. We have to increase the amount of items that we're working on at one time. So, this gives us a blueprint. This gives us tools by which we can improve the process, depending on how we want to get it done. Now, let's take an example process. Here we have a discount optical shop. So we have 5 steps. First, we greet the patient, and that takes a grand total of 2 minutes. We get the customer's information, write it down, take insurance information, all of that fun stuff. And then we have the eye exam. Now, the eye exam takes 25 minutes, and we can work on one customer at a time. Then, once that eye exam occurs, we have the frame and lens selection. So the customer looks through all the lenses the frames are available, choose the various types of lenses that they want, and that takes about 20 minutes. And then we get to the glasses made step, and the glasses made step takes an hour, but we can work on up to 6 customers at a time. We can work on up to 6 pairs of glasses at a time. And then there's the final fitting. They bend this wire here or there, and that takes 5 minutes. So we can work on one customer at a time there. So, we have a set of tasks. We have an inventory, the number of customers that we can work on at one time. And we also have a flow time for those particular steps. Now, let's make it a little interesting and say that our business brings in, on average, $400 in revenue per customer served. Something to think about. After all, ultimately, we hope to make money with this. Hopefully, we intend to generate value with this particular process. Well, it's a good idea to get a measure of the value generated by this process and the value generated by improving the process. So that we have some yardstick, some measurement by which to see how well our process ultimately improves the bottom line. So, the first thing we do, we use Little's Law. We have inventory, we have flow time, so we calculate a throughput rate. So, for the greet the patient step, we're able to work on one customer at a time. Takes 2 minutes. 1 divided by 2 equals 0.5 customers a minute. For the eye exam, we're able to work on one customer at a time. Takes 25 minutes. 1 divided by 25 is 0.04 customers a minute. So we calculate the throughput rate for each step of the process by taking the inventory divided by the flow time. So we have throughput rate for each step. So, to reiterate the calculations here, throughput rate equals inventory divided by flow time. So, for the glasses made step, flow time is 60 minutes. Now, we can work on up to 6 items at a time. So, as long as our task isn't starved or blocked by something else, our inventory is going to be 6. As a result, we can find our designed throughput rate for that step. And again, the design throughput rate is the throughput rate through that step in the process if it is not being blocked or starved by anything else. If it has as much work as it possibly needs. Well, in that case, the throughput rate is inventory divided by flow time. It's equal to 6 glasses divided by 60 minutes, or 0.1 glasses per minute. So I just want to clarify again what's meant by designed throughput rate. Design throughput rate is what the process could do, or what a step in the process could do, if it didn't have to worry about anything else. If it didn't have to worry about being starved, didn't have to worry about being blocked, didn't have to worry about anything, could just work and wasn't being stopped by anything. That's a designed throughput rate. So our actual throughput rate, how much it's actually getting done, well, this could be less than that. That may be less than the design throughput rate. That said, again, remember that Little's law always holds. So if the actual throughput rate is smaller, then either the inventory or the flow time will be smaller, usually the inventory. So again, if we work with a customer only half the time, then our average inventory will be 0.5. So oftentimes, if the actual throughput rate is smaller than the design throughput rate, it means that the actual inventory is smaller than the designed inventory, because we're not busy all the time. Now, suppose we want to improve our process. Well, we have inventory of 6 glasses. We can work on up to 6 glasses at a time. We have a flow time of 60 minutes. So, assuming that the task isn't starved or blocked, well, that means that we can produce 0.1 glasses a minute, or 1 pair of glasses every 10 minutes. That said, what if we increase our inventory? What if we increase the number of glasses that we can work on at one time? Say from 6 up to 10. Well, that changes our throughput rate. And if we increase our inventory from 6 up to 10, that increases our throughput rate from 0.1 glasses a minute to 0.167 glasses a minute. Well, this gives us a blueprint. It gives us a method by which we can increase the throughput rate for this particular step, and ultimately increase the throughput rate for the entire process. Now, here's a visualization of the process. We have 5 steps. We have a throughput rate for each step. This is not a particularly good process. Good way of thinking about it, the greet register the patient step, it takes 2 minutes for them to get done, and then they're waiting for the next 23 minutes. So because you have these wide differences between the throughput rates, you're going to have a lot of idle time. You're going to have a very low utilization, and we'll talk about utilization later, for the first step, for the greet register the patient step. What we want is a throughput rate that is similar, that's balanced throughout the entire process. And hopefully we can improve the process such that we can get exactly that. So, remember, the throughput rate of the process is the minimum of the throughput rates of the individual steps. So, whichever step in the process has the smallest throughput rate, that's going to limit the throughput rate for your process. So, in this case, we're able to produce 0.04 glasses a minute, or 1 pair of glasses every 25 minutes. So, this is our bottleneck, what we call our bottleneck. This limits the throughput rate for our process. Now, if we were to work 8 hours a day, the amount of revenue we could make in a day, well, $400 per customer, times 480 minutes, times 0.04 customers per minute, well, that comes to $7,680 per day. That said, we can do better. So, how do we improve things? How do we balance the process? Well, what we can do is we can look at Little's Law. We can effectively manipulate the process using Little's Law in order to get the throughput rates for each step as close as possible. So how do we do this? Well, we can add people to the process. Keep in mind this does cost money, so we do need to weigh that. Or we can redistribute people along the process, redistribute equipment perhaps, or perhaps we could combine parts of the process. There are multiple options available for changing the conditions of the process. So, we decide to improve our process by adding 2 people. Where do we add them? Well, we add them to the only places that will improve the process. We add it to the bottleneck. So the first person goes to the step in the process with the smallest throughput rate. So we add it to the bottleneck, we add it to the eye exam step. So we hire a second optometrist. So instead of working on 1 pair of glasses at a time, we're able to work on 2. So our new throughput rate, if inventory goes from 1 pair of glasses to 2, well, that means that our new throughput rate is going to be 2 glasses divided by 25 minutes, or 0.08 glasses per minute. So our new cycle time for this particular step is going to be that 1 divided by 0.08, so 12.5 minutes per pair of glasses for that step. It's important to remember that this is just for that step. We're going to see how it affects the entire process in just a second. So, why the bottleneck? Well, the reason why the bottleneck goes back to that idea that we're only as fast as our slowest step. If we're only as fast as our slowest step, the only thing that can improve the process, the only thing that can make our process faster, is to improve the bottleneck. So, the capacity of the process can be increased only by increasing the throughput rate at the bottleneck. Improving the process at any other place will not work. So, throughput rate of the process is determined by the throughput rate at the bottleneck, so help in any other portion will not help us. So, we aim our help at the activity of the process with the smallest throughput rate. In other words, if we can only go as fast as our slowest step, we make sure that that slowest step is faster. So, we've added 1 person to our process. We have a new throughput rate for our conduct eye exam step. So, what's the new bottleneck? How fast can this process go? Well, it turns out that we have a new bottleneck in this case because, well, while the conduct eye exam step can now go much faster, well, it turns out that the new bottleneck is at the frame and lens selection step because that still has a design throughput rate of 0.05 glasses a minute. So because this is now our smallest throughput rate, this becomes our new bottleneck. So if we want to add a second person to the process, and we want to improve the process, guess where we're going to do it. That said, before we get that far, let's tally up the profit. Let's see how much this improvement to our process actually makes things better. Well, if our new throughput rate is now 0.05 customers a minute, that means that we're generating $9,600 revenue per day. So, if the cost of adding another person to perform an eye exam is less than $1,920 per day, $9,600 minus $70,680, then it's probably a good idea. We should probably get it done. So, if we want to add the second person, we add it to our new bottleneck. We add it to the frame and lens selection step. So we have another person working there. So we're able to work on 2 pairs of glasses at a time. So with a new inventory of 2 at the frame and lens selection step, this gives us a new throughput rate. 2 glasses divided by 20 minutes, that's 0.1 glasses a minute, or 10 minutes between each pair of glasses. So we have a new throughput rate of 0.1 glasses a minute. So let's see what this does to our process as a whole. Well, now, the conduct eye exam step is the bottleneck again. However, you'll note that while it is still the bottleneck, our throughput rate is much greater. And you'll note that the process as a whole is much more balanced. It's not a case where people are waiting around so much in this particular process. For instance, while some things can't be fixed, you'll note that the throughput rates through this particular process are a lot more equal now. They're a lot more even. And it's balancing that process, making the work far more even through a process. That is what we're hoping to do. So we have a much healthier process as a result. So, by adding a second person to the frame and lens selection step, well, we see that our revenue has increased fairly dramatically. We see that our new revenue per day, well, with a throughput rate of 0.08 customers a minute, well, 0.08 customers a minute, $400 per customer, times 480 minutes, well, we see that we're generating $15,360 in revenue per day. So, the second person, adding the second person to the frame and lens selection step, well, that will net us $5,760 more per day than what we were looking at with just adding one person. Now, we do need to have a caveat here. After all, we play to win the game. If demand and supply are high enough that it's worth it, then we should add more people. However, remember, it is possible to be starved by supply. It is possible to be blocked by demand. As such, whatever we get done, it needs to have a purpose. It needs to generate value. So, any improvements to our process need to be able to generate value, And thus, only if demand warrants it, only if demand warrants this increase in the throughput rate to 0.08 customers per minute, only then should we make this improvement. Thank you, and have a good day.